Welcome to the Deep Dive, your essential shortcut to knowing exactly what matters in the world of groundbreaking science and discovery. Today, we're really opening the door at a field of chemistry that's fundamentally rewriting the rules.
Mm.
We're talking materials science.
Yes, specifically molecular architecture. It sounds fancy, but it's about building materials molecule by molecule.
And the results are, well, pretty astonishing. Imagine materials that can pull drinking water right out of thin desert air.
Or store really explosive gases like hydrogen safely at, normal pressures.
Or even clean up those toxic forever chemicals, the PFAS stuff, from our water much more effectively than before.
It's a huge shift. For years, chemists looking for a material for a specific job, filtering, catalysis, whatever, they'd search nature or use existing synthetic stuff, often rigid, sometimes unpredictable.
Right, sort of hoping to find the right tool.
Exactly. But now, chemists are becoming the architects. They're designing these materials from scratch, literally piece by piece, creating these tiny, incredibly organized, well, molecular rooms, you could call them.
Molecular rooms, I like that. Tailor-made for a specific chemical job.
Precisely. Whether it's a reaction or just storing something.
And that massive change in approach, from just finding stuff to actually engineering it.
Mm-hmm.
That's why we're here today,
Mm-hmm.
because the big news just dropped. The Nobel Prize in Chemistry for 2025, it's been jointly awarded to three pioneers, Susumu Kitagawa, Richard Robson, and Omar M. Yaki.
And the award citation says it perfectly. For the development of metal organic frameworks.
Metal Organic Framework.
Yeah.
MOFs. You're going to hear that acronym a lot.
You are. So what are they? Think crystalline structures. But the key thing is, these crystals aren't solid blocks. They're full of vast, organized, repeating holes or pores.
Like a scaffold.
Exactly like a molecular scaffold, built from metal bits acting as, say, cornerstones and organic molecules acting as the struts linking them together.
Okay.
It gives chemists this incredible level of control over matter. We're talking materials with internal surface areas and chemical properties that just, well, they weren't really conceivable before MOFs came along.
Okay, so let's unpack this properly. Our mission for this deep dive is to explore the history, the thinking behind it, and the really quite amazing future of these MOFs.
We'll trace the journey. It starts, believe it or not, with something like wooden models in a classroom.
Seriously?
Yeah. And ends up with materials many are calling the defining materials of the 21st century.
So we'll see how these three laureates, Kitagawa, Robson, Yagi, how they took a really clever idea that didn't quite work initially
Right, the stability problem.
and turned it into something real, something practical. And crucially, what this breakthrough means for tackling huge global challenges: climate change, energy, water.
It touches all of those. It's a fundamental new tool in the chemist's toolbox.
Right, let's start with the basics then. Building materials. You need the plan, the components. What are the absolute essential pieces of a metal organic framework?
Okay, it breaks down nicely, just like the name suggests. You've got the metal part. These are usually metal ions, think zinc, copper, cobalt, acting as the nodes, the corners of the structure.
Got it. Metal corners.
And then you have the organic part. These are generally longer molecules based on carbon. They act as the rigid linkers, the struts connecting those metal corners.
Little nodes, organic struts.
Exactly. And when you get them to link up in the right way, they form this highly porous, very regular crystalline structure, like a repeating cage almost.
And the person who first really saw the potential of using these two parts to create that kind of geometric order, that was Richard Robson, right?
Thank
Way
you.
back in the 70s.
That's right, Richard Robson. And his eureka moment is just a fantastic story. It happened in 1974 purely by chance, almost.
Accidental genius.
Pretty much. He was teaching at the University of Melbourne. And he wasn't setting out to invent some revolutionary material. He was just getting stuff ready for a standard chemistry lesson.
What was he doing?
He needed models, the old
Oh.
ball and stick models of molecules. He asked the university workshop to drill holes into wooden balls, the atoms, so he could stick in wooden rods, the chemical bonds, to show students molecular shapes.
Oh, okay. I remember those from school. But you can't just drill holes anywhere, can you? Atoms have specific ways they connect.
Precisely. That's the whole point of the models. Each atom type forms bonds in a very specific geometry. Carbon likes 4 bonds in a sort of pyramid, a tetrahedron.
Right.
So Robson had to carefully mark out exactly where the holes needed to be drilled on each atom ball to respect that fixed geometry.
Makes sense.
But then, as he started putting the models together, sticking the rods into the pre-drill holes, bang, the insight hit him.
What was it?
He saw that the finished models, these complex 3D molecules, they just automatically form the correct structure. Why? Because the fixed positions of the holes dictated the overall geometry. The rules were built in.
Okay, that's neat for a model, but
Yeah.
what made that jump from a teaching aid to a potential revolution in making actual materials? Surely people knew about molecular geometry.
Well, absolutely. But applying it to designing large, complex, predictable structures, that was different. Chemistry back then, especially synthesis, was often, well, messy.
Heat it and hope.
Kind of. You'd mix things, apply energy, and often get a mixture of products, impurities. It wasn't always well ordered. Robson realized he could take that principle from the wooden balls, the fixed geometry, and scale it up.
How?
Not just linking individual atoms, but linking together pre-designed larger molecular units, whole building blocks with their own inherent rigid geometry.
Ah, so using the shape of the pieces to control the shape of the whole construction.
Exactly. If your building blocks are rigid and have fixed connection points, the overall structure has to follow that predefined pattern. It was about imposing order through design.
Instead of the usual chemical chaos, the bird's nest, as you called it.
Precisely. And he finally got around to testing this idea properly much later in 1989. He needed a model structure known for perfect order. He chose diamond.
Diamond, the ultimate example of rigid ordered structure. Carbon atoms perfectly locked together.
Right. Each carbon bonded to 4 others tetrahedrally. Perfect repeating pattern, very compact. Robson wanted to mimic that pattern, but using his new, bigger building blocks.
So what did he use instead of carbon?
For the cornerstones, the nodes, he used positively charged copper ions, specifically Tex2 plus $. Like carbon, these copper ions naturally prefer to be surrounded by 4 neighbors, a tetrahedral coordination.
Okay, so copper ions, the corners. What are the links, the struts?
He needed something with 4 arms to connect to the 4 points around the copper. He chose a specific 4-armed organic molecule. Each arm ended with a chemical group called a nitrile.
And nitriles like copper.
They have a strong, specific attraction to those Tex2 plus ioners, so the geometry matched perfectly. A 4-point node, copper, and a 4-armed linker, the organic molecule. Everything designed to fit.
It sounds so logical. But you said most chemists still expected it to fail, to just make a mess. Why?
Because getting such relatively large, bulky molecules to neatly assemble into a perfect crystal, it usually doesn't happen. Normally, thermal motion, solvent effects, competing reactions, they just overwhelm the subtle geometric instructions. You'd expect a random powder, an amorphous gunk.
But it worked.
It worked beautifully. Because the geometric matching was so precise, the copper ions and the linkers effectively found each other and locked into place. They self-assemble into a regular crystalline lattice, just like Robson predicted.
Okay, so he made a crystal based on the diamond structure. But what was the big deal? What made it different?
The space, that was the crucial, groundbreaking difference. A real diamond is incredibly dense, almost no empty space inside. Robson's crystal, however, it was mostly empty space. It contained this vast network of large, repeating cavities or pores running throughout the entire structure.
Like a diamond framework, but hollow.
Essentially, yes. A diamond made mostly of air, held together by this precise molecular architecture. That was the world's first real metal organic framework, a MOF.
And did he show it could do anything?
He did, quite quickly. He showed that small molecules and ions could move in and out of these cavities. He demonstrated ion exchange, for instance. He immediately saw the potential, talking about catalysis, new materials with properties never seen before.
But there was a catch, wasn't there? The reason it didn't take off immediately.
The big catch, stability. His initial constructions were, well, the term used was quite rickety.
Rickety.
Yeah. When he tried to empty out the cavities, remove the solvent liquid that was present during the synthesis, which kind of propped the structure up.
It collapsed.
Often, yes. The framework would just fall apart. Imagine building a beautiful, intricate sandcastle. Looks great when it's wet, but when it dries, poof.
Right. Not very useful if it disintegrates the moment you try to use its empty space. So the scientific community, they weren't convinced.
Largely, no. It was seen by many as this elegant, intellectually interesting curiosity, but ultimately useless for practical applications. A beautiful failure, in a way.
So he'd laid the conceptual groundwork, the blueprint, but the materials themselves weren't robust enough?
Exactly. And that lack of stability meant the field kind of stalled for about a decade. People needed MOFs that could stand up on their own, empty and ready for use. That was the challenge left for the next generation of innovators.
And this is where, as you said, it gets really interesting. Robson gave us the vision, the proof of concept. You could design these incredibly porous structures, but making them stable, making them dynamically useful. That took the parallel, sometimes overlapping, but distinct breakthroughs from Susumu Kitagawa and Omar Yagi.
Okay, let's tackle Kitagawa first. Working in Japan through the 90s, and apparently he had this really interesting philosophy driving his work. Something about the usefulness of useless.
Yes, that's a recurring theme in his story. It's inspired by the ancient Chinese philosophers Wangzi. The idea is to look beyond immediate, obvious utility and find value in things that might seem pointless or flawed at first glance.
Which must have been handy, because wasn't he facing the same skepticism Robson did? His early MOFs weren't exactly world beaters either. Not at all. His initial efforts, around 1992, also used copper ions, like Robson. He created a two-dimensional material that could trap acetone molecules, which was, interesting.
Yeah.
But it wasn't particularly stable and didn't have a clear, compelling purpose. It certainly wasn't enough to convince funding agencies.
Right. It must take incredible persistence to keep pushing in a field when everyone, especially the people holding the purse strings, is telling you it's a dead end because the materials literally fall apart.
Immense persistence. His grant applications kept getting rejected. The feedback was consistent, too unstable, no clear application. But Kitagawa was convinced there was something profound there. He just needed to find the right building block.
He needed stronger connections, better molecular glue.
Essentially, yes. He realized the copper ions Robson and he himself had used might not be forming strong enough or perhaps geometrically suitable enough bonds to create robust, three-dimensional frameworks that could survive without the solvent.
So what was the breakthrough moment for him around 1997?
It was. His group made a crucial switch. They moved away from copper and started using different metal ions: cobalt, nickel, or zinc.
What are those metals?
These metals, when combined with a specific organic linker molecule called 4-bol-4-bipyridine, formed genuinely stable three-dimensional structures. The combination of these metals and this linker created bonds that were strong enough and arranged in the right way to hold the framework together even after the solvent was removed.
They didn't collapse when dry.
They didn't collapse. This was huge. They created stable 3D MOFs with open channels running through them. And crucially, they showed these empty, stable frameworks could do exactly what was hoped. They could absorb gases.
What kind of gases?
Common industrial gases, methane, nitrogen, oxygen. They showed the MOFs could take them up, hold them, and then release them over and over again without the structure changing shape or degrading. This was the proof of stability and function that the field desperately needed.
Okay, problem solved. Stable MOFs achieved.
Stability, yes. Function, yes. But Kitagawa realized there was another hurdle. He needed to clearly define why these new MOFs were special. Why weren't they just, fancier versions of existing porous materials?
Like zeolites, I've heard of those. They're used in industry, right, for filtering and stuff.
Exactly. Zeolites were, and still are, incredibly important industrial materials. They're made from silicon dioxide. They're very stable, very porous, great at absorbing gases. So the question was, what makes MOFs better, or at least significantly different? If they're just another rigid sponge, why bother?
Good point.
Yeah.
What was Kitagawa's answer? What made MOFs unique in his view?
He articulated this really clearly around 1998. The key difference, he argued, boils down to customizability and functionality.
How so?
Zeolites are essentially fixed structures dictated by their inorganic chemistry. There's a limited range. MOFs, on the other hand, because you construct them from metal nodes and organic linkers, you have a potentially enormous library of organic molecules to choose from.
Thousands of different possible linkers.
Tens of thousands, even more now. This means you can rationally design the MOF. You can tune the size of the pores. You can change the chemical environment inside the pores by adding different functional groups to the linkers. You can build in specific properties.
So zeolites are like standard off-the-shelf components, but MOFs are like custom-designed, precision-engineered tools.
That's a great analogy. But Kitagawa took it even further. He introduced a truly revolutionary concept about the nature of MOFs themselves. He proposed they could be soft materials.
Hang on. Soft. We're talking about crystals. Crystals are the definition of hard, rigid things. How can a crystal be soft?
Right, it sounds contradictory. But what Kitagawa realized and demonstrated was that unlike the completely rigid framework of zeolites, you could intentionally build MOFs using certain flexible organic linkers, or design them so there were weak cooperative interactions within the structure.
And what does that flexibility allow?
It allows the MOF to change its shape in response to external stimuli. He showed that some MOFs could dynamically open or close their pores when guest molecules like gases entered or left.
Whoa. He famously described this behavior as being somewhat like a lung that can breathe gas in and out, changeable but stable, a molecular lung. That's a powerful image. So it's not just a static container, it's dynamic, it responds.
Exactly. It moves MOFs beyond just simple storage into the realm of dynamic function. Think sensing or highly selective separation, where the material adapts to grab only one type of molecule. He introduced the idea that these materials weren't just structures, they were potentially responsive systems.
Okay, that's a massive conceptual leap, flexibility and responsiveness.
Yeah.
Meanwhile, across the globe, Omar Yaghi was taking a different but equally important path, wasn't he? More focus on pushing the boundaries of rigid structure and rational design.
That's right, Omar Yaghi. His story is also quite remarkable. His background, growing up in Amman, Jordan, facing significant challenges.
Yeah, the notes mentioned quite difficult circumstances, a single room, no electricity or water at times.
It really highlights his incredible drive and determination. His fascination with chemistry apparently sparked really early, around age 10. The story goes he snuck into a locked school library, found chemistry books, and was just captivated by the diagrams of perfect ordered molecular structures.
That image of perfect order must have contrasted sharply with his surroundings and maybe even with how chemistry was often done in practice.
That seems to be a key motivation for him. He saw traditional chemistry, the heat and mix approach, as inherently chaotic, often leading to impure products, unwanted side reactions. He craved control, precision.
He wanted rational design.
Exactly. He wanted to be able to design a structure on paper, choose the exact chemical building blocks like snapping together pieces of Lego, as he put it, and know that the final product would be precisely what he intended. Clean, ordered, predictable.
And he started making progress on this in the mid-90s, building structures and, crucially, giving the field its name.
Yes. By 1995, his group was successfully linking metal ions and organic molecules, initially creating these two-dimensional net-like structures that used copper and also cobalt.
And the cobalt one was particularly good.
It was. It showed really impressive thermal stability. It could handle temperatures up to 350 degrees Celsius without decomposing, which was very high for these kinds of materials back then. And it could host guest molecules within its structure.
And this is where the name came from.
Correct. In the paper describing these findings, Yaghi and his team formally coined the term that stuck, Metal Organic Framework, MOF.
So he named the field and demonstrated high stability. But the one MOF that really became the poster child, the one that made everyone sit up and take notice, that was the MOF5, right? Around 1999.
MO5.
Yeah.
Absolutely. It's considered a classic for a reason. It combined exceptional stability with unprecedented spaciousness.
How stable was it?
When empty, it could handle temperatures up to 300 degrees Celsius. This was the kind of robustness Robson had dreamed of but couldn't achieve. This proved MOFs could be seriously durable.
But it was the space inside that really blew people away.
Oh, yeah. The statistic that made researchers, as the Nobel release puts it, raise their eyebrows. That was the internal surface area.
Let's hear it again. The football pitch analogy.
It's just astounding. Take just a couple of grams of MOF5 powder, like you said, maybe a few sugar cubes worth. If you could somehow unfold all the internal surfaces within that tiny amount of material, the total area would be as big as a football pitch.
Wow. A football pitch inside a sugar cube. That's hard to even visualize.
It is, and that number just dwarfed the capacity of existing materials like zeolites. It showed that MOFs weren't just a novelty, they offered a fundamentally different scale of porosity, an enormous internal surface packed into a tiny volume.
Why is that huge internal surface area so important?
Because that's where the action happens. For storing gases, filtering liquids, or catalyzing reactions, you need surfaces for molecules to stick to or interact with. More surface area means vastly higher capacity.
Right, more parking spots for molecules inside the MOF.
Exactly. Yaghi's MOF5 was like building a multi-story car park with incredibly thin floors and walls, maximizing the parking space relative to the building materials.
So we have these two major threads. Kitagawa focusing on stability plus flexibility, the breathing MOFs.
Right, for dynamic functions, selectivity, responsiveness.
And Yaghi pushing for maximum rigid stability and sheer storage capacity, exemplified by MOF5. Are these competing ideas?
Not really competing, more like complementary. They demonstrate the incredible versatility of the MOF platform itself. It showed you could tailor the design for different needs.
So if you need massive gas storage, you want Yaghi's rigid high surface area approach.
Precisely. For storing methane for vehicles, for example, you want maximum capacity and stability. You don't necessarily want the container changing shape. MOF5 set the benchmark for that.
But if you need selective separation or sensing, maybe Kitagawa's flexible MOFs are the way to go.
Exactly. The lung-like MOFs are better suited for tasks where the material needs to actively respond or adapt to its environment. It showed the breadth of what MOF design could achieve.
And Yaki really cemented this idea of MOFs as an engineering platform in the early 2000s, didn't he?
Hmm.
Showing you could systematically modify them.
Absolutely. That was a final piece of the foundational puzzle. Around 2002-2003, he demonstrated the power of rational modification. He didn't just make MOF5, he made a whole family of related MOFs.
Oh.
By systematically changing the organic linker molecules, he used linkers of slightly different lengths. By doing this, he could precisely tune the size of the cavities inside the MOS structure.
Like choosing different length Lego bricks to build different sized rooms.
Perfect analogy.
Yeah.
He created 16 distinct variants of MOF5, each with slightly different pore sizes.
Yeah.
This allowed him to optimize the MOFs for specific tasks, like finding the ideal pore size for storing the maximum amount of methane gas for natural gas vehicles.
So it wasn't just one lucky discovery. It was proof that chemists could now sit down, design a MOF with specific properties on paper, choose the right building blocks, and actually synthesize it. They were truly becoming molecular architects.
That's exactly it. The combined work of Robson, Kitagawa, and Yagi provided the blueprint, the stable materials, the diverse functionalities, and the rational design principles. They built the foundation for an entire new field of chemistry.
So let's bring this into the present and future. We have Robson's initial vision, Kitagawa's stability and dynamic flexibility, Yagi's rational design and massive capacity. What does this toolbox actually let us do? You mentioned tens of thousands of MOS exist now. Where are we seeing the impact?
The impact is starting to become very real, moving from academic labs into potential and in some cases actual commercial applications. And a huge focus, understandably, is on environmental solutions and resource management.
Okay, like the water harvesting example. That
Mhm.
sounds almost like science fiction. MOF 303 from Yagi's group, pulling water from desert air in Arizona.
It sounds incredible, but it works. It leverages the MOF's ability to selectively absorb molecules. MOF 303 has internal surfaces that are chemically tuned to grab onto water molecules, even when there aren't many around, like in very low humidity air, below 20% sometimes.
So it just sucks the water vapor out of the air?
Essentially, yes. It acts like a super sponge for water. It typically does this overnight when temperatures are cooler. The MOF holds onto the water tightly.
And then how do you get the water back out to drink? Squeeze the MOF.
Not quite. The elegance is in the release. It's designed for low energy input. When the sun comes up and heats the material.
Ah, solar power.
Exactly. The warmth provides just enough energy for the MOF to release the trapped water, but now as liquid potable water. It's a passive capture and release cycle driven by natural temperature swings.
Wow. So you could potentially have devices working off-grid in arid regions,
Right.
just making water out of the air using sunlight.
That's the vision, and the prototypes have shown it's feasible.
Yeah.
Decentralized water production where pipelines or wells aren't an option, it's potentially transformative.
Absolutely. Okay, beyond harvesting resources, what about cleaning up messes? Environmental remediation. You mentioned PFAS, the forever chemicals.
Yes, PFAS are a huge problem. They're in so many products they don't break down easily, and they contaminate water sources worldwide. Removing them efficiently is tough.
And MOFs offer a better way. How?
Two main advantages: selectivity and capacity. A MOF, like UIO67 for example, can be designed with pores that are just the right size and have the right chemical stickiness to selectively grab PFAS molecules out of water, even when they're present at very low concentrations.
Better targeting than, say, standard carbon filters.
Often, yes. And remember that massive surface area. That means they have a much higher capacity to hold on to the pollutants before needing regeneration or replacement. A small amount of MOF can clean a lot of water.
Can they also destroy the pollutants, not just trap them?
Some can, yes. That's another exciting area. MOFs can be designed not just as sponges, but as catalysts.
Catalysts, meaning they speed up chemical reactions.
Exactly. So a MOF, like MLO101, which has these enormous internal cavities, can incorporate catalytically active sites. It's been used to help break down stubborn pollutants like components of crude oil spills or even trace antibiotics found in wastewater.
So instead of just collecting the waste, the MOF helps destroy it.
That's the goal, turning harmful chemicals into simpler, less harmful substances. It could make water treatment much more efficient and sustainable.
Okay, shifting to energy and climate change. Carbon capture is obviously a massive priority. How do MOFs fit in there?
They're extremely promising. The challenge with carbon capture, say from a factory smokestack, is selectively grabbing the carbon dioxide while ignoring all the nitrogen gas, which makes up most of the exhaust.
You need a tech CO2-specific filter.
Precisely. And MOFs can be designed for that kind of selectivity. CALF20 is a great example. It's engineered with pore sizes and surface chemistry optimized to preferentially absorb tech CO2.
And is this actually being tested at scale?
It is. CALF20 is undergoing trials right now at an industrial facility in Canada. The hope is that its high capacity and selectivity will make direct capture of text CO2 from emission sources much more economically viable. It's a direct tool to fight greenhouse gas emissions.
What about the other side of the energy coin, clean fuels? Hydrogen comes up all the time, but storing it is a major headache. It's explosive under high pressure.
It's a huge bottleneck for the hydrogen economy. Storing hydrogen gas safely and densely requires very strong, heavy, expensive high-pressure tanks. That's a barrier for vehicles, for example.
Can MOFs help here? Do they avoid the high pressure?
That's the key advantage. MOFs offer a way to store hydrogen at much lower, safer pressures closer to normal atmospheric pressure, or maybe slightly elevated.
Now, where does the hydrogen go?
It doesn't rely on squeezing the gas molecules together with brute force. Instead, the hydrogen molecules stick to the vast internal surfaces inside the MOF, pours through relatively weak physical absorption forces. Think of it as lining the walls of those molecular rooms with hydrogen.
So the MOF acts like a sponge, soaking up hydrogen at low pressure. A material like Nu-1501 does this.
Exactly. Nu-1501 is one of the leading materials optimized for this. It can store significant amounts of hydrogen at near ambient pressures and release it readily when needed.
Okay, but here's the crucial question. Can it store enough hydrogen? How does the density compare to those high-pressure tanks, even if it's safer?
That's the critical trade-off and the focus of intense research. Historically, MOFs stored less hydrogen by volume than the best high-pressure tanks. But materials like Nu-1501 are really closing that gap. They're getting much better.
So maybe not quite as much hydrogen packed in, but way safer and cheaper.
That's often the calculation. The massive improvement in safety, avoiding dangerously high pressures, and the potential reduction in tank weight and cost could make hydrogen vehicles or other applications like renewable natural gas (RNG) vehicles that might use MOFs for methane storage much more practical for widespread use. It de-risks the whole system.
Makes sense. Safety is paramount. Beyond these huge climate and energy applications, are MOFs finding uses in other industries?
They are. Their ability to handle tricky gases is valuable. The semiconductor industry, for example, uses some extremely toxic gases in manufacturing microchips.
Right. Handling those must be a nightmare.
MOFs are being used as highly effective filters or scrubbers to capture these toxic gases, or even as safe storage containers for them, significantly improving safety in these high-tech facilities.
What about defense applications? Chemical weapons?
Yes, that's another area. Researchers have designed MOFs that don't just absorb harmful chemical agents, but actively break them down. The MOF structure can incorporate catalytic sites that rapidly decompose nerve agents or other chemical weapons upon contact.
Like a self-detoxifying filter material.
Something like that. A critical technology for protective gear or decontamination systems.
And you mentioned earlier, they can even keep fruit fresh longer.
Ah, yes. On a less dramatic note, some MOFs are very good at trapping ethylene gas.
The stuff that makes fruit ripen.
Exactly. So, incorporating these MOFs into food packaging could potentially slow down the ripening process and reduce food spoilage.
Fascinatingly diverse applications.
Yeah.
And what about medicine? We touched on the soft MOFs. Could they deliver drugs inside the body?
That's a really exciting frontier, linking back to Kitagawa's flexible MOFs and Yagi's precise structural control. The idea is to load drug molecules inside the MOF's pores.
Like cargo containers.
Exactly. Then you design the MOF so it only releases its cargo under specific conditions found where the drug is needed, maybe the specific pH level inside a tumor, or triggered by temperature or light.
Targeted delivery. So the drug goes right where it's needed, minimizing side effects elsewhere.
That's the promise. More effective treatments with fewer side effects. It's still in development, but the potential is enormous.
It really seems like from water and energy to medicine and manufacturing, these MRFs are popping up everywhere. Is it fair to say they're moving towards being a major industrial material?
I think that's definitely the direction of travel. Major chemical companies are investing significantly now in scaling up production and developing commercial applications. They're using both the rational design principles from Yagi and Kitagawa, and now even AI and machine learning to discover and optimize new MOFs even faster.
So the material of the 21st century prediction might not be hyperbole.
It might not be. The ability to design materials with this level of precision and functionality is truly a paradigm shift.
The work of these three laureates hasn't just given us new substances, it's given chemistry a whole new way of thinking about building matter.
Absolutely. It aligns perfectly with Alfred Nobel's intent conferring the greatest benefit on humankind. They've given chemists the tools, this molecular architecture, to start tackling some of our most difficult and long-standing problems in fundamentally new ways.
This has been an absolutely fascinating deep dive. Let's try and quickly synthesize the key contributions before we wrap up. We started with Richard Robson.
Right. Robson provided the initial spark, the proof of concept. He showed you could build these vast, ordered, porous crystals using metal corners and organic links, the blueprint, but
But they were unstable, rickety.
exactly. Then came Susumu Kitagawa. He solved the stability problem, finding the right metal linker combinations. He demonstrated they could actually absorb and release gases without falling apart.
And crucially, he introduced the idea of flexibility.
Yes, the revolutionary concept of soft MOFs, materials that could change shape, act like a lung, enabling dynamic functions and selectivity, a whole new dimension.
And finally, Omar Yagi.
Yagi gave the field its name, MOF. He pushed stability and rational design to the limit, creating the ultra-stable, incredibly spacious MOF5.
The football pitch in a sugar cube.
That one. Proving the immense capacity possible. And he demonstrated the power of systematic modification, showing chemists could truly engineer these materials for specific tasks. The complete toolkit.
Blueprint, stability, flexibility, capacity, and engineering control. All essential pieces.
Their combined insights really did launch a new era in materials chemistry.
Okay, for our final thought. We talked quite a bit about Kitagawa's concept of MOFs acting like a flexible lung, breathing gases in and out, changing shape based on what's inside. That idea of a material dynamically responding to its molecular environment is powerful.
It really bridges the gap between static materials and dynamic systems.
So here's something for you, our listeners, to think about. If we can now build materials that mimic a biological function, like breathing absorption, response, release, what comes next, what other complex biological functions could molecular architects eventually translate into stable, human-made materials?
Could we see materials that, say, repair themselves when damaged, like skin? Or materials that actively regulate temperature, like biological organisms do?
Or even materials capable of basic information processing, responding to sequences of chemical inputs? How far can we push this biomimicry using molecular architecture? Where does the line between a smart material and something resembling a living system begin to blur?
It's a fascinating question about the future possibilities opened up by these architects of molecular rooms.